So we have a realistic scenario here where there is a source with a source impedance and a transmission line, lossless transmission line of impedance Z0 and L, and there is a load impedance ZL, right. So everything that we learned so far told us that as we move away from the load and towards the generator, the impedance locally that you can replace it with, right, keeps changing, and we had the expression for what this impedance was as a function of length given by this expression ZL cos beta L plus J right. So this is to say that the voltages and currents and their behaviors on this transmission line is not constant, right. The amplitudes of their oscillations and their phases change as we go along this transmission line, and this can be captured, right, as saying that mathematically it is like truncating the transmission line at a different position L not equal 0, and then replacing the ZL with the Z as a function of L that we have here at that new location, right. So just to pictorize what I just said, this impedance transformation right is capturing the idea that there are constructive and destructive interferences, and if I were to truncate the load at some point, say L prime, I can just replace ZL with Z as a function of L estimated at L prime, right. So these two circuits and their behaviors will be identical, right. So that is what this impedance transformation is all about, okay. And this fundamentally is explained due to the constructive and destructive interferences of what we call V plus and V minus waves, right, and establishing some sort of a standing wave pattern on the transmission line at high frequencies. So if we take L prime all the way to the length of the transmission line and transform the impedance to as seen at the beginning of the transmission line, right. So I'll call that point A. So if I were to transform it all the way to the generator, let me say I get an impedance that is ZL prime, right. This is essentially just Z estimated at the length, full length of the transmission line. Okay. So this is something that you are already equipped with, right. Now the question is, what is our V plus? So we are going to say at point A, now we can just use the Kirchhoff's current and voltage laws that you were taught, right, to analyze this just as a lumped circuit, because all the transmission line effects have been taken care by this impedance transformation, right. So I can simply just say that the current flowing through the circuit is the source voltage divided by the total impedance, and then the voltage across the load is quite simply the current multiplied by ZL prime. So that's Vs times ZL prime divided by Zs plus Zl prime. Okay, so you can essentially estimate Ia and Va, right, in any problem that you are given. Once you transform the impedance to the generator, then you can use your simple circuit laws, right. Then we also know that this Va at the beginning of the transmission line must have been the sum of so I am using small l as a variable as well as the length of this transmission line. So maybe let me make this into d, right. So let's say d is the distance or d is the length of the transmission line. That way we can sort of remove any confusions. So we are going to say that this is e to the j beta d plus gamma L V plus e to the minus j beta d, right. So remember, gamma L can be complex, right, and gamma L is simply reflection coefficient estimated at the load. Okay, so you can just take out V plus e to the j beta d common, okay. So this is your Va as written in form of V plus, right. So we can equate 1 and 2. Remember, Vs, Zl prime, Zs all are knowns, right. So Va is known. The only unknown here is V plus phasor, right. All other terms are known. Even gamma L is known, small d is known, beta is known, right. So everything between equations 1 and 2, everything except the V plus phasor is unknown, right. So you can simply combine the two and get the expression for V plus. Okay, I will let you substitute Va with Vs, right, because Va is a temporary voltage that we used. You can certainly get V plus in terms of all the known quantities, that is Vs, Zl prime, Zs, gamma L and small d, and of course beta for the transmission line should be known. Okay, so this is the simple procedure for you to estimate V plus in any scenario. Once you know V plus, you can essentially give me the voltage, current and power, average power dissipated at any point along the transmission line, right. So you should be able to give us the full picture. Okay, so hopefully by this time you have gotten a very good idea of how to use the lossless and distributed model for transmission lines in order to describe the behavior of constructive and destructive interferences with these so-called voltage waves and current waves, right, in order to establish the voltage and currents and power at any point along the transmission line. Okay.